Hello everyone, my name is Rosan Upreti.
Hi, I'm Prince Guru.
Hi, I'm Karma Guru.
So today I'm presenting our research. The topic of our research is AI-powered honeypot for the cyber threat detection. So with my teammates Prince and the Karmav. So in this semester we did a research, like how to protect our server and our like a modem and all of our internet device from the cyber threat. So mostly we focused on the honeypot algorithm. So what we did is we just we programmed a Raspberry Pi and connected with it with the external display and connected it with the server throughout the internet cable. So we created the program in such a way, and we install the web server and we implemented the honeypot algorithm so that whenever the hackers try to steal our data, so there will be like some kind of like a hoax will be created within the server so that instead of the actual data, the hacker will get another data. So that's the one part, and another part is we have integrated our system with the OpenAI, I mean like a ChatGPT API. So whenever like there is such kind of error, so we'll get those error from the log error, and those texts will be analyzed by the ChatGPT, and we will get like the actual, what's the problem and what's the solution in the external display.
Some of the problems are limited to proactive detection, and it includes AI-powered analysis. This means it's real-time interpretation of threats, and it also includes honeypot deployment, and it just means attracting and capturing attacker behaviors. And it also includes traditional security, so it only gives limited visibility into novel attacks. As cybersecurity became more advanced, defenders need better visibility into attacker methods and faster ways to react. Traditional security infrastructures has limited proactive detections capabilities, struggling with novel attacks or producing high volumes of alerts, requiring expert analysis. While honeypots can capture the full behavior of attackers, manual analysis of honeypot logs is slow and requires specialized knowledge. Small organizations often lack the budget or expertise for enterprise-grade security solutions, and our research addresses the need for cost-effective, automated threat detection system that can both gather detailed attack data and interpret it immediately.
Research objectives. Here's what we set out to do. Um, Number one, we deploy Gaudi and Dynea honeypot on a Raspberry Pi, analyze attacks using ChatGPT to classify behaviors like brute force, malware, or scanning, visualize the activity with Grafana dashboard and a Flux backend, automatically block attackers using fail to ban and add IP tables, evaluate performance in terms of accuracy, responsiveness, and system load.
So we just distinguish like our research in like a different part, so the first one is like the honeypots and the deception technology, suppose like the hackers they try to steal the data, there are like different kind, they will also do different type of social engineering, maybe they will just send us like a phishing link or anything like that. So those are the things, so those are like the first part, how we tackle the hackers using the honeypot. And the second one is like a cyber threat, so maybe like the hackers they won't do the honeypot, maybe the hackers, maybe not like some kind of like a hacking, like those that maybe maybe those things cannot be prevented by the honeypots, so we have we use the like open AI API. So basically how it works, suppose the IP, like the web server is running, and if our system it detects, there is like something happening, there is like unusual traffic coming from something like that. So those things, those things we have integrated, like the LLMs we have integrated in our system. So if any of those things happen, so it will detect and it will send us like a message to either usually it send the message to the admin, so basically like as I said. So we install everything in like a Raspberry Pi, and the external display is connected with that. So anything happens, it will be shown in that one. So like talking about like integrated and the monitoring response, like so we have like all of this like internet sales and all of this, like the fail to ban and everything, like, and so that these things, like so these things basically prevent the system from being hacked, or like try if like prevent from those prevents from the hacker, like who wants to gain like unauthorized access of our system.
Some of the background, wait. Some of the background and related works we did was the hardware platform you used is called Raspberry Pi, like my friend Rosen mentioned before. And we also use Kauri Honeypot and Dioneea Honeypot, as well as we use systems as Suricata IDS and TCP dump. This helps with identifying like incoming hacks. And also we integrated ChatGPT API, and we also did some visualization and automation.
System architecture. We integrated all components on a single Raspberry Pi. All components run on a Raspberry Pi with a single network interface. Forwarding exposes Gauri and Dynea parts to the internet, while the Flux and Grafana services are internally accessible or protected by VPN. The system integrates multiple components. Gauri and Dioneea generates logs for the attacker interactions. Suritica monitors all traffics. The ChatGPT module parses logs and sends prompts to the API. Flux API serves event data. Grafana visualizes attack timeline and fail to ban enact firewall bans based on thresholds.
So, like, so you might wonder, like how we did our research and like how we implemented. So the first things, like, so the for the system setup, like the first things that goes is like, like it's like basically we set up like a Raspberry Pi. So we use the Raspberry Pi 4 because, like there is like integrated Wi-Fi and the internet also. And just to make it like more better, like we just use the internet cell to connect with the server, like so that everything goes perfect. And another thing is, like we just use the external display that I said earlier. So after that we install, like before installing the web server, we install the Linux server within that, so that, like we just say, so instead of installing like the maybe like Windows server or anything, we just went with the Linux server and we use the CentOS distro. So within that, like we just install like a bunch of like all of these things like a CoreWrite and Dioneea. So like we just deployed that one, and like we configured like a fail to ban and like some Python script, and like we integrated like all of these like we used the like all of those like API and everything, and we just like wrote the Python script so that we can get all of the log error and everything, and we all those data we sent it to the OpenAI's API, and we got all of those data in the return. So as I said, like we installed the web server, so that like we just created like a basic web page so that we can just show it on the display. And like a testing phase, like suppose we build the system, like we just need to we just went with like a few debugging and like a QA session. So like it's like we just did ourselves, we did like a brute force method, and we did the DDoS attack, so that like at least we can know like how, if like our system is working or not. And for the metrics and the collection, we just track how these things are working, like if the fail to ban and other things are actually working like that, and if like how the latency of the network is it like really working, and it's like really able to prevent the hacker from entering our system.
We also did an AI analysis performance, and the accuracy from this analysis was that we generated 50 thread summaries with which also resulted in approx 96% deemed accurate upon expert review. The system successfully identified attack patterns, malware behaviors, and attacker intentions. And some of the minor issues included occasional overstatements, and such as mislabeling a simple script as a rootkit in some instances.
Automated response and visualization. The first one is automated blocking. The system implemented 320 IP bans via filter ban during the test period. Notably, 70% of the banned IPs did not return post-ban, suggesting effective deterrence. Banning thresholds were carefully calibrated to balance data collection and defense needs. No false positive bans occurred on benign admin IPs, demonstrating the system's ability to distinguish legitimate from malicious activities. The second one is real-time visualization. Grafana panels successfully displayed attack timelines, geographic attack origin from over 40 countries, AI analysis summaries, and system performance metrics. The real-time update interval of 10 seconds provided timely information without overloading the Raspberry Pi's resources. The visualization components made the complex attack data accessible and actionable for security personnel. And the final one is system performance. Despite the resources constraint of the Raspberry Pi platform, the system maintained good performance metrics. The CPU utilization averaged 30% of idle time, with spikes to 80% during the stress test. RAM usage remained under 4 GB with no swapping required. Network capture averaged approximately 50 MB per day of PCAP data, demonstrating efficient resource utilization.
All right, so here are like a few things, like case study. So, like we just use like some of the, like I said, like we tried like some like ethicals hacking, like we just to test our systems. So when a telnet login was, accomplished by the Mirai by a Mirai, like the bot was detected, and then the AI, what we integrated to our system, like. Those like those all of those behavior were like successfully detected, including like the specific command and patterns, to that really helped, like to identify the vulnerable device and the subsequent payload delivery mechanism. And the system also provided the contextual information about the Mirai botnet's typical target and the potential impact, and enabling us, so which that really help us to, to get to find the issue more easier. So another is human intruder, so during the reverse shell attempt, the AI summary detail the attacker's persistence mechanism and the reconnaissance steps, like it correctly distinguished this more sophisticated human driven attack from automated scanning. So basically what does it mean, like suppose like so maybe some people, maybe they don't want to steal our data, but like they are just doing like a DDoS attack, so they want to like they are just giving us like unusual traffic and they want to shut down our site. So this really help, because those things have like those things have like a specific pattern, like so they are just like pinging us from, like they are just giving us the ping, from their site. So which could so basically if there is like a more load to the server, those things could really go down, but these things it really help, so that we could our system it detect, it really detect like how these things are going, like in how specific mechanism it's going at, and it helps us to realize like what is going on. And then there is like the analysis, like the all of these analysis, it help, it help, like to minimize the risks, and like the from our like or ChatGPT API, and it gives us like a few steps, like how can we prevent this type of actions.
Discussions. AI augmentation reduces analyst time by summarizing logs and inferring intent. It also helps by real-time active defenses, honeypot from passive research to operational tools. It is also very cost-effective, and it demonstrates feasibility for SMEs and distributed sensors. Synergy of tools, honeypots, IDS, AI. These yields better coverage and confidence, ethical deployment, maintain attacker data privacy, and prevented misuse of honeypot. Limitations include protocol coverage, hardware constraints, AI dependency, and potential stealth attacker invasion. Geo, next one.
Ethical consideration before deploying any security system, especially one that interact with real world attackers. It is crucial to address the ethical implementation implications. In our project, we took several important steps to ensure responsible and lawful deployment. Our system was designed with ethical responsibility in mind. Although attackers have minimal privacy expectation, we still treated all the collected data with care. We ensured legal compliance by keeping the system passive. There is no hacking back or outbound misuse. To avoid entrapment, we didn't lure attacker with the fake promises, just expose vulnerable looking services. AI outputs were labeled as advisory with human outside in place to avoid misjudgment. And finally, any malware sample were captured, were handled responsibly, shared only when necessary, and without revealing any identified IPS.
So there are like obviously there are like so lots of limitation, like because we are just doing the research. So instead of making the full product, we were just working to make like a MPV only, so there are the first one is like the limited protocol coverage, so obviously right now we are just we have the hardware and we are just putting it on each of the server, that's obviously not the convenience way, and another is the crowdy high interaction is stimulated, maybe those things, if whenever if the hacker are highly experienced, maybe first time they attack they will get alert, but from the next time they will know we have installed the honeypot algorithm, so they will find the different way, they will just skip that path and they will just access our account, all of the info and data with the another way. And the third one is the dependence on the external API, so basically the first one is the latency, because we are using the open AI system, so obviously maybe sometimes their system can go down, so those things are the thing. And maybe because of some of the internal issue, the latency, so maybe the response time will be really high. And the second time is the cost, so the cost is really depends, how much we are going to. So if we every time, if we just send the request, we keep it refreshing every minute or every second, so how is how in how large, how much in scale we are putting it, so that's the cost is going to be more. And the third one is outages, like I said, so there might be some kind of issue in the ChatGPT API, or maybe they will just change, maybe there might be a maybe they just change their system and we need to do few updates in our core like that, so anything can happen, and so fourth thing is so maybe we are using the AI, so these things AI, these are so these are basically the prompt engineering, so sometimes the log here the AI maybe they cannot understand those things, so maybe from that one also, the things, what we are getting the output from the open AI API that might not be 100% true. And there is a Raspberry Pi, like we mentioned earlier, so but when we did the research, the the uses of the RAM was below the 4 GB, because but the Raspberry Pi that we used, it has the RAM capacity of 4 GB, so if really went more than that, our things will get down, like then we need to set it up everything from we need to install and to configure all of the algorithm and all of the system from the beginning, and sometimes like some of the things we wrote the script, right? So those things, like we need, if something happens, so we need to manage and redo everything. And sometimes like the whenever the server get into the maintenance or like something happens, so those things are really hard.
Some of the conclusions and some of our future directions are so it demonstrated feasibility. So we successfully integrated Honeypot's AI analysis and automated response on resource constrained hardware, creating a versatile security sensor that both detects and interprets cyber threats. And some of the key innovations we are able to conclude were AI augmentation reduces analyst time by summarizing logs and inferring intent, and real-time active defensives honeypots from passive research to operational tools. And this is also a very cost-effective platform, demonstrates feasibility for SMEs and distributed sensors. Some of the future directions we are taking is we can expand honeypot coverage to web, database, and IoT services. Explore on-device LLMs for offline analysis, implement real-time AI-driven honeypot responses and adaptive behavior, create a network of collaborative honeypots, and share intelligence. While not a replacement for comprehensive security measures, this AI-powered honeypot system serves as a powerful augmentation for research and defense.
Acknowledgement. We thank our academic mentors, especially our Professor Ileti and our lab colleagues for their guidance and collaborations. We appreciate the open source developers behind Kauri, Dainia, Suri, Kata, Grafana, and Feltuban. We really acknowledge the support of our institution for the hardware and the computing resources. Finally, we are grateful to the cybersecurity community for inspiring the work and contributing the research that underpins our system.
So here are some of the reference, so as we were writing, all of these paper and everything, we tried our best to so all of these things this we got like references. We try to get it from from reliable source. Got it from like Google Scholar. And if you look at them, most of them are from the paper those were published in IEEE. So yeah, so most of these things what we did, what we found out, those things are like from the very reliable source. So yeah, this is our presentation for this for the research project. So if you have any question or if you want to know more about our project, you can just let us know. Thank you.
Thank you.
Thank you.